what do you think is meant by the linear velocity of a carrier gas? What's a carrier gas? What is that? So we're talking about gas chromatography. The carrier gas is probably the what phase? The mobile phase. And then linear velocity, Mel, is probably just what?
Going straight to the column.
Yeah, it's flow rate. It's speed, right? So many meters per second or centimeters per second. Okay, so Alyssa, different carrier gases operate most efficiently at different, what would you guess? Linear velocities. Okay, so it has everything to do with viscosity. You would think that just like different liquids have different viscosities, you know, they flow naturally at different flow rates, so do gases. Is hydrogen safe to use as a carrier gas, Andy?
Yes.
Yeah, I guess any gas is under pressure may not be safe, but you have to handle it correctly.
It's flammable gas.
Yeah, it's flammable. So, I've been Googling. I looked this morning trying to Google where, you know, what do you do with a compressed gas cylinder in a fire? They have these release valves and things. So I think as long as it's not damaged, it won't explode. But take a look at this video of when one's damaged. He backs up, yeah, smart guy.
He's trying to get as far as possible.
Like nobody behind it.
Yeah. That's funny that he was recording it at the perfect time. Yeah.
I thought they showed those cylinders flying around, but I guess not. I could have stopped this a long time ago. Ooh.
Yeah. I think they're
Alrighty. So
no.
well, that's damage, though. So it says all the time, all the damage. How about this one? We're back to Andrew. At least blank analyte molecules must exist in the vapor phase at the designated pressure and temperature of the inlet. Otherwise, a non-volatile residue will be left behind in the blank.
Is it 100?
It's actually 1. Needs to be somewhat volatile. Not very volatile, but at least 1. Otherwise, it's non-volatile residue will be left behind in the Inlet, right? Because that's where everything's supposed to be vaporized. Brandy, what was gas-liquid chromatography again? Yeah, the mobile phase. Well, the mobile phase is the gas pushing it through.
Yeah. But the column is like lined with it or something.
Yes, the column is lined with a
Liquid.
liquid, right? You have that glass capillary column, and then you've got this liquid in there. Okay. What is the headspace when referring to a liquid, Melissa?
Didn't you talk about this last time? It's like right above it?
Yes, and it makes the most sense if it's sealed. So you've got this liquid,
And then like the vapor is like in the head.
and this, you got to seal the cap. You need to, otherwise the headspace is going to be everything, right? So if you seal it, put a cap on there, then it makes more sense what the headspace is. Okay. Alyssa, the mobile phase in gas chromatography. Does that make sense, what we were talking about? You can't really see the drawing what I was trying to draw. Right? You have a liquid. There's the headspace right here. Right? The mobile phase, Alyssa, in gas chromatography is often referred to as a carrier gas because it sweeps away the analyte molecules present in the headspace and carries the molecules down the until the molecules diffuse again into the stationary phase. So they're going into this liquid phase, and they're going into the mobile phase, and they're going into the stationary phase, mobile phase, stationary, and they only move when in the mobile phase. So this whole time, things are going down the, where's all this happening? In the column, yeah, and this whole affinity idea between mobile and stationary phase. Andy, in gas chromatography, all analytes spend the same amount of time in the mobile phase. Andrew, as the temperature is increased in gas liquid chromatography, more molecules move into the, as the temperature is increased, in gas liquid chromatography, more molecules move into the
Column? Stationary?
Would it be the headspace?
So you're cranking up the temperature.
Wouldn't it be mobile phase? But
Mobile phase isn't, yeah, the answer should be mobile phase, right? But it's not a choice. But it is actually there.
stationary?
It's
Column.
headspace.
So wouldn't it be like vaporized? It'd be
Yeah.
chilling above
Because remember, our stationary phase is the liquid. Right. So the headspace is going to be immediately above it. So you're right. Going into the mobile phase is the headspace. So the answer is headspace as you crank up the temperature. So as the temperature is increased in gas liquid chromatography, more molecules crank up the temperature, they move into the headspace, they get into the mobile phase, and in turn these molecules will elute, anybody? Faster, right? Because they're in the mobile phase. So crank up the temp if you want to get done faster. Below are two cross sections of gas liquid chromatography, capillary columns, A and B. So the dots are the analyte. Each contains, they're the exact same compound. In which column will the analyte elute faster? What would you guess, Brandy? A or B? Yeah, B, because there's more in the headspace or mobile phase or gas phase, right? Headspace is the best word you're supposed to use since it's a liquid there. Melissa, since the analyte is the same in each column, what possibly could give rise to the difference occurring in the two columns? Everything's identical. Something is different, though. Temperature, exactly. Which one's hotter? B is hotter. Alyssa, in order for the analyte to move through the column, the temperature of the column must be the boiling point of the analyte.
Above?
Above?
Oh yeah, didn't we say that it has to be hotter? Like in B, the temperature is higher than it is in A.
No, we said it needed to be hotter. It needed to be really hot. What part of the GC needs to be really hot? Only the inlet. You want to vaporize everything. Okay, so that's really hot, above the boiling point, everything vaporizes. Why don't you have to keep, and you don't have to keep the oven. This is a misconception. You don't have to keep the oven really hot. If ethanol boils at 70 degrees Celsius, you can run that, and you've done this. You've run the column just above room temperature, 40 degrees, and you get all of these solvents off, and their boiling points are way over 40.
Doesn't matter.
It doesn't matter. Why doesn't it matter? How does that work then?
It's already vaporized. It's already a gas.
Once it enters the inlet.
But does it stay a gas? Remember, it's going through gas, going through this liquid layer. It's going to have an affinity for the liquid layer, depending on how like dissolves like, right? So different compounds will have different affinities for that liquid layer. So they'll go into the liquid layer, come out, right? So they'll have they'll be in either the stationary phase or in the headspace. There will be an equilibrium going on there. Some will have a higher affinity for the stationary phase, that liquid. But the point is you don't have to be above the boiling point. Things will happen faster if the hotter it is, but it doesn't matter. For a gas-liquid chromatography elution, a single analyte is injected at a temperature well above its boiling point. Okay. And the oven containing the column is operated at a gradient, initially well below the boiling point. So it's injected at, the inlet's doing its job. That's what they're trying to say. The inlet is really hot, inlet did its job. And then everything gets vaporized, enters the column, which is in the oven. The oven containing the column is operated at a gradient, which means what's changing? Since this is gas chromatography, what's changing? If you hear the word gradient, the temperature of that oven is changing. Initially well below the boiling point of the analyte, but reaching a temperature well above before the analyte elutes. Sketch the distribution of the analyte molecules at the beginning, middle, and end of the column. So what could you do to illustrate this temperature gradient? Knowing that it's beginning not very hot, at the end, oh, it's hot, really hot.
They're going to be more attached to the stationary phase of the beginning.
Yeah, exactly. Just draw a bunch of more dots that are inside or touching that liquid. All right. Now I wouldn't draw them all there, because if you draw them all there, it's not moving. You're not showing that there's anything in this mobile phase. So draw, I don't know, one or two, right? And then in the middle, just what? Have a few more in the middle. In the end, have all of them in the middle, right? Something like that, or whatever you think is appropriate. Okay. Different peaks have different sharpness in GC chromatograms. Andy, what do you think is meant by sharpness? In other words, some are narrow while others are wide. What are they talking about?
How narrow it is.
What's the it?
The peak.
Peak. Yeah. Signal versus, what's the x-axis in these times? So these chromatograms? So a nice sharp peak would be something like that, right? There's going to be some width to them, but it'll be a nice sharp peak, nice and symmetric on both sides, really sharp. The peak shape is decided on what the analyte is doing at the blank of the column. What would you guess there, Andrew?
Throughout the column.
Throughout? Everybody agree? It's the end. All that matters is what's happening at the very end. Because remember, we already said that things are changing. So I can visualize a really sharp peak if it looks like this at the end. If it doesn't look like that at the end, not going to be very sharp. So with the cross-section of a gas-liquid column A, in the column A, use dots to illustrate the distribution of analyte molecules that would result in a very sharp peak. And then with the cross-section of a gas-liquid column B, use dots to illustrate the distribution of analyte molecules that would result in a very fat peak. So what would be the difference between the two? Is the very end of the column, you have a really sharp peak.
With all the molecules in the headspace.
In the headspace. Very well said. Right? Fat peak. Andy, now what?
There would be more molecules in the stick to the side and fewer in the middle.
Yeah. So they're still in the liquid phase. You have to boil them off to get them off. And there might be. Just draw a bunch in there. So with these pictures in mind, Brandy, does it seem that it's possible that too much sample can be injected on a column? We talked about too much sample being injected on the inlet. We call it sample overload and how everything couldn't instantaneously vaporize and get onto that column right away. So they're not talking about that. They're talking about the column. Yeah. I mean, you can physically see it. There's only so much room, right? The liquid is only so thick. It's going to have a capacity. Yeah. So, Mel, what would you guess? Which, if any, has a higher capacity, a large or a small diameter GC column? Larger. I would say that too, right? Because you'd have more mobile phase. Sorry, you'd have more stationary phase, right? Physically, you'd have more. Right? Do you think liquid chromatography, Alyssa, columns, liquid chromatography, do you think they also have a capacity? Yeah, because it's a physical restriction. I mean, there's only so much stationary phase. So yeah.
Was number 6 yes also?
6.
Yes.
Yeah. So if they have a capacity, then yeah, you could inject too much. Yep. Okay, so time is money. And Andy, one way you could lower your bill of paying these guys is just to make stuff elute faster. And you can just crank up the pressure in the column. And because you have all these little buttons on the GC you can set. And set that inlet pressure really high. Okay. And then the flow rates, everything goes up. But why is a high pressure a bad thing to have, especially in the inlet of a GC? Hint, think about vapor pressure. It's a tough question. There's another hint, a little boiling pot there.
If it comes out of the machine too fast, they might all just be, all the peaks might be too close together.
Oh, yeah, that's always a possibility. But they're saying that There you can mess with temperature though, and you can do a gradient and fix the problem. The problem here is even worse. This problem can't be fixed. This problem is, to me, the limitation of GC. Why could GC only take 20% of compounds in the first place? Right, where LC there's no limit. It can take whatever compounds you want to inject in there as long as the detector can detect it.
Does it have to do with like molecular weight?
Had to do something with molecular weight.
Of
Why?
Compounds you inject? Because it can only hold, what is it, 400?
Yeah, 400 grams per mole is another way of saying it. Why? If the GC, your analyte has to be in what phase?
Gas.
Gas phase. How do you get something in the gas phase? You
Vaporize.
vaporize it. You boil it, right? Whatever word you want to use. You really heat it up. Okay. And the reason for that 20% or that 400 grams per mole is some things just do what when you try to heat them up?
They don't vaporize?
Either they won't vaporize because, it's physically, these engineering, you can only handle 300 degrees is the highest these typical inlets go. Either it won't vaporize or it does vaporize, but what happens? It dissociates, it decomposes, it does something that it doesn't stay the way it's supposed to. So you have all these issues going on. That's why you've got this limit of 20%, or just in a general rule, definitely 400. Anything over 400 grams per mole, you don't even try. You're just wasting your time. Okay, so the pressure idea. Everything's hunky-dory. Right? We inject it, and things are going great. We can see our peaks. It's just that it takes so long. I want to go faster. So you mess with the temperature in the oven, and yeah, it's okay, but it's still so slow. You crank up the pressure in this inlet. In other words, you crank up the flow rate of the mobile phase. The same thing. That's the only way to crank up the pressure. The only way to crank up the flow rate is to crank up the pressure. And the pressure starts in that inlet, so you're cranking up the pressure in the inlet. What happens with boiling points with pressure? If you crank up the pressure, what happens to the boiling point? It increases, right? You go to Colorado, up on the mountain. The atmospheric pressure there is what in comparison to us? It's lower. So will their water boil at 100 degrees? No. Can they get the water 100 degrees? If you remember your general chemistry, it'll be a lower boiling point. So they got to boil their macaroni for 30 minutes instead of 20 minutes, whatever, right? Because they can't get the water as hot. But they can do what to make it boil at 100? Now you could do a little pressure cooker thing, and that would work. But you have to go buy the instrument and all that stuff. Add something. Add anything to the water. Any solute will make boiling points of solvents go up. So, but the point is, with this story, is you crank up the pressure in the inlet. All you're doing is now you got to heat it up even higher for it to vaporize. Well, then you have all those same issues. Is it going to vaporize? Is it going to decompose? So it causes, you're just enhancing the limitation of the GC by cranking up that pressure.